Okay. So today we will do the last antenna which is there in our syllabus, that is the reflector antennas. Okay. So reflector antennas is basically a two element system. There is the main antenna, which is the feed, and there could be one or more than one and reflectors, which are not itself antennas, but they are used to uh, for better directivity, better point the signals that are radiated by the antenna. Okay, to increase the directivity also to some extent. So the most common reflectors, they are, so suppose I have got a planar, this is a metal plane, and this here is an antenna. The antenna is giving some signal out, and this will get reflected by the plane like this. Sorry, this shadow will be in this direction. So this is a very basic planar reflector. Is it okay? However, you can see that this planar reflector cannot be used so much to focus the beam towards any given direction. Okay. There can be some other reflectors as well. For example, this is called a corner reflector. This is our feed. The feed is radiating signals which is reflected by the corner reflector. Okay. This angle is sometimes 90°. Is it okay? This is by simple geometrical optics, right? You have studied geometrical optics in school. It's same, more or less the same thing. Okay. The more common reflector antennas that are used in EM theory, they are, first is called the front fade reflector. So this is my reflector. This is my antenna. Okay. This point is called vertex. And how it will work? Now, if you, which reflector? Okay, this is called a curved reflector. This is called corner reflector. This is my feed. The feed can be a horn antenna. Okay, it can be some other antenna as well. Here we can say this. Now, there is a principle from coordinate geometry that you might have studied in your school, that if there is a point at the focus, okay, then upon reflection, the reflected line would be parallel to the axis of parabola. So this principle is used in the parabolic reflector antennas. So this feed is always at the focus of the parabola. Okay. and so whenever beams are reflected from it, they are always parallel to the axis. Okay, and that is the way we can have at the same time, if the signal is coming as a receiver antenna, you must have seen curved reflector antennas are very common. uh, can you tell me where do you see curved reflector antennas? You must have seen. It's very common. It's available. It can be seen anywhere. Can you give me an example of a curved reflector antenna? Can you give me an example of a curved reflector antenna? Where can you find curved reflector antennas in practice? It is available in most people's home. Yes, exactly. Dish antennas, DTH. Okay, dish antenna is one big example. Uh, for example, if when you go out of the college, there is a GSI big office just the other side of the road. You will find big reflector antennas. So another very good example is the DTH antennas. Okay, so DTH antenna, there is a big plate, but that plate is not the real antenna. The plate is simply the reflector. The real antenna is that antenna that is focusing on the plate. Okay, you will see the connection is always with that antenna which is connected by a rod to the plate. Sorry, connected by a rod which is pointing towards the plate. Okay, that is the real antenna. The big disc you see where the company name is written, that is actually the reflector. This type of feeding is called front feed. This could be quite obvious that it is fed from the front, and as a when it is used as a receiver, what happens? The satellite is quite very far away from the antenna, so the rays from the satellite, they are almost parallel to the axis. Okay, and then again from the same principle, upon reflection, all the rays, they converge at the focus where the original receiving antenna is kept. Okay, that is how a satellite antenna works. Is it okay? Any questions regarding this? Exactly, you can see this is an example of a reflector antenna. Right. This is the reflector. Okay, and this is the original antenna which is kept at the focus. So any beam that is coming from the long distance, okay, upon reflection, it passes through the focus where the antenna is kept and is reflected by the antenna. Okay, that is how we can have a much larger directivity. Okay, okay. Another very common feed type is called the Cassegrain feed. How is that works? It's, here there are two reflectors instead of one, and the feed is here at the center. Okay, this is called the main or primary reflector, which is parabolic. Main or primary reflector. Okay, there is a second reflector here which is called the secondary reflector or a sub reflector. So what happens? The ray, it comes, it gets reflected by the first by the secondary reflector, then by the primary reflector, and it is like this. Okay, this is called the Cassegrain feed. Okay, exactly right. You are absolutely correct. It has actually come from the Cassegrain telescope. So you are right. The principle is the same. Okay. So any questions regarding this? So these are the main four type of reflectors that we can see. It could be the corner reflector, it could be the curved, the front fade, or it could be the Cassegrain feed. What is the disadvantage of the front fade reflector? Can you tell me? What is the disadvantage of a front fade reflector? Which one? Which one do you want me to explain again? What? Which one? Last one. Okay. This is also a curved reflector, but the feed here is a bit different. The feed here is the Cassegrain feed. Okay. For Cassegrain feed antennas, there are two reflectors and one feed. The main feed is at the center of the primary reflector. The primary reflector is parabolic in shape. Okay. This is parabolic. There is also a secondary reflector which is hyperbolic. Okay. So what happens? The signal is radiated by the feed element. It is first reflected by the secondary reflector. Then it is reflected by the primary reflector. Okay, in such a way that the final reflector wave is parallel to the axis. Okay, so there are two reflections. First one is by the secondary, and the second one is by the primary. Is it okay? The basic idea of any reflector is to collimate the beams, rays. What is collimation? Collimation of rays. What is that? Collimation of rays means to make the rays getting in a parallel formation. Usually the is parallel to the axis. Okay. Our aim is to make the rays becoming parallel to each other. See here, the rays are parallel. Even for the parabolic reflector, see, collimation is achieved. The reflected rays are all parallel to each other. Okay. Now, can you tell me that can a log periodic antenna will be used as the feed of a parabolic reflector? What is the advantage or disadvantage of that? Do you understand the question? Can we use a log periodic antenna as the feed of a parabolic reflector? What would be the advantage or disadvantage of doing that? What is the advantage or disadvantage of having a log periodic antenna as the feed of the parabolic reflector antenna? What do you think? How does the log periodic antenna works? We have discussed. Okay, I'm drawing it very casually. It is the exact lengths we have already discussed in the class, that how they should be. It is like this. Okay. And how it works, there was an active element. Okay, the active element was moving. When the frequency was reduced, the active element was moving towards the left, towards the longer elements. And when the frequency was increased, the active element is moving towards the right. Okay. So think in this way. What will be the problem now if we have a log periodic antenna as the feed? What will be the problem? The problem would be that, as we discussed, if the frequency is increasing, we are moving towards left. If the frequency is increasing, we are moving towards the right. If the frequency is decreasing, we are moving towards the left. Okay, but the focus is the same point, right? So in order to, for the antenna to practice to function well, as we have discussed, the feed should be in the focus. Okay, but if the active element moves with the change of the frequency, obviously it will be out of focus for most frequencies, right? So the efficiency of the antenna would be less. That is the reason why log periodic antennas are not very commonly used as the feed of antennas, parabolic reflector antennas. Is it okay? Is it okay? So this will always be at the focus of the reflector. Acha. Single reflector antennas usually have an aperture efficiency. Remember aperture efficiency? What was aperture efficiency in the first class we discussed? What was aperture efficiency? What was the directivity of the antenna? Directivity of the antenna was D equal to 4 pi AE by lambda square. What was AE? What is this AE? 4 pi is obvious. Lambda is the wavelength. That is also very obvious. What is AE? Exactly, effective aperture. Right. Right. Absolutely correct. It is the effective aperture. And the effective aperture is related to the physical aperture by the aperture efficiency, or AE equal to eta by AP, where AP is the physical aperture. This can be actually measured. This is called the aperture efficiency. So D is equal to, combining these two equations, D is equal to 4 pi eta AP by lambda square. So obviously more the value of eta, more will be reflectivity. Okay. So for single reflector antenna, eta is usually 50 to 60%. For Cassegrain, it is 60 to 70%. This was single reflector. For Cassegrain, it is usually 60 to 70%. Is it okay? There are a lot of derivations and big equations, so those things are not required at this level. Just know how it works, that will be fine. Okay. Any other questions regarding this? Okay. Uh, any other questions? I think that is more than enough for this reflector antennas, and I think that more or less covers our syllabus for the